So thank you all for having me here. I'd like to tell you a bit about the verification of subsets of Rust, and also highlight a bit why I'm not doing the whole language at the same time. But first, I want to say a little bit about what we've been doing at the COBRA Center. So this is the Concordium Blockchain Research Center in Aarhus, which is part of Aarhus University in Denmark, where we have a big research institute supported by the Concordium Center. So this should work better like so. Yes. So I've been part of Concordium from the start. So we help to as scientific advisors, we help to set up the project, and this was very exciting. But then after some time, we found out that there was actually a lot of basic research that needed to be done. And if you look at this this thermometer here, so this is the usual stages of how to the technology readiness level. So there's very basic research, which is at the bottom here. So that's the boiling stuff, and then slowly things get cooler. And what has been extremely exciting in Concordium is that we both have the possibility to do the basic research here at the COBRA Center, but that we've been able to work very closely with experts like Thomas to translate this very basic research to things that actually run in production. So this has been very exciting that we're able to do this and to have a very close collaboration. We write papers together. We have joint seminars. We're actually sitting physically quite close to each other. So we're sitting at the university, and the Concordium company, to a large extent, sits across the road from us. So we can easily walk back and forth between ourselves. So the COBRA Center, we have many experts in cryptography, secure distributed systems. There are five staff members and lots of postdocs and PhD students involved. Also quite a few people that are not directly paid by the Concordium Foundation. There's a big, vibrant community. In my group, we're doing formal verification, smart contracts, and high assurance cryptography. And this is done by the following people: Daniel, Milo, Jakob, Benjamin, Nikolai, and Philip. Some are postdocs, some are PhD students. And what, as I said, what is very important is that Concordium is actually based in very basic science and also very new science. So some of the papers that came out were implemented very quickly. And then I'm excited about this DevX initiative that we recently started with Benny and Ernest as a collaboration between Concordium and the COBRA Center. Just to say why formal verification is important in this context, we want to avoid bugs. Some of the very serious projects actually, they had bugs in cryptography, and this allowed people to print money. And because this was a project where everything was anonymous, they couldn't actually trace whether this happened or not. And it was possible just to print an unlimited amount of money. So this is something that we really, really want to avoid in this context. On the other hand, there's also bugs in smart contracts. Thomas just showed you a very simple smart contract, just tic-tac-toe. But people have actually put millions and sometimes tens or hundreds of millions of dollars or euros in these smart contracts. And then when people made small programming errors, people could actually steal millions, tens of millions, 50 million, 100 million of dollars from these smart contracts. So it's very important that we try to avoid this. there was already a very good question. How does the Concordium language, the Rust language, smart contract language, how does it differ from Ethereum? Well, the type checker. So Rust is a very serious language. It comes from a long tradition, long academic tradition, the ML family, and takes a lot more other academic insights. So it's really a very well-developed, very well-developed language with many many well-thought-out IDs. So the type checker already helps you an awful lot to write correct programs, and this is something that you all know as Rust programmers. Of course, we like to discuss on Zulip, and I invite you to join us talking about formal methods on the stream, the dedicated stream on Zulip. We started to discuss more about reviving the Rust formal verification working group. And so there's a lot of knowledge about formal verification also in the Rust community. Most of you will know unit test. A lot of you will have used property-based testing, things like quick check, prop test. So these are all very good starts, and formal verification just goes one step further in that direction. There are two ways of doing this. There's automatic and interactive formal verification, and this is really a spectrum. So the automatic tools can prove some properties of software, as you would expect. But if you want to do very advanced proofs, then you need a human to interact with a computer proof assistant. And the examples, I'll mention a few examples. So things like a verified compiler for C or ML, a hypervisor. There's a lot of work going on there, and this is actually used in military helicopters. And then, of course, the smart contracts, where I'll talk about. Interactive formal verification is the state-of-the-art in programming research. So if you want to develop, if you want to write a paper for a conference like POPO, which is the flagship conference on programming language design, then about 40% of the papers there actually come with a formal proof. So you want to prove properties like this program actually does what it's supposed to do, so it's functional correctness, properties about programming languages, so things like type safety. If you're thinking about compilers, this could be preservation of semantics. So these kind of properties you want to prove about your language. And this is also really a tradition where Rust was developed. But before I get into Rust, let me say a bit more about the proof assistant that I'm using. So, and there are a number of other proof assistants that do something similar, but this is a very old and venerable one. So the Coq proof assistant has been around for 35 years. It's a functional programming language. So to a large extent, it's part of the ML family, just like Rust. But on top, and it has a very powerful type theory. So on top of the regular type theory, you can also use the type theory as a logic to actually directly write specification of your programs. And I'll say a bit more about this. I have a small illustration here. I don't know. Oh, yes, you can actually see my mouse. So here's how you would write, define lists and define head and tail of a list. And then you can make a predicate. So this is a specification of when an element is actually in a list. And as you see, this doesn't look too different from what you would write in Haskell or in Rust. The Coq proof assistant has a very small kernel. It's about 5,000 lines of code. And those are all the logical rules. So they're just the basic axioms of mathematics. And those have been checked. There's a program going on to check the system in itself, just like you would write a compiler for a language in itself. The system is used by tens of thousands of users. There's a big community with lots of discussion going on Zulip. If you want to know more about the proof assistant, there's a series of books, Software Foundations, and most of you should be able to just read the start of those books. They're very good for self-study. So if you're interested in this kind of topic, there's an easy way to get in. And once you start reading the books, just come and join us on Zulip, and people would like to discuss. Here's a very biased state-of-the-art of formal verification in Rust. Unlike C, there's no precise Rust semantics. So C has a big Bible where that really writes down what a C program should do. For Rust, this is currently lacking. But there's a very exciting project called Virocene that actually tries to develop this and tries to do versioning for Rust and try to specify at least some subparts of Rust. Then, of course, there's the WebAssembly, which has a very precise and formalized semantics. So this really was developed within the context of these academic conferences that I mentioned. I was actually in the program committee when this was first formalized in the certified proofs and programs, the POPL, but such designs of new languages is something you could send to POPL or ICFP, such academic conferences, and WASM was actually very carefully designed, and this is really a very beautiful piece of work. Then there's LLVM, of course, which is used in the Rust toolchain. There's a project called Vellum, which is tries to formalize and specify parts of that. And there's a very big project called Rustbelt, which tries to give us semantics for something called MER, the intermediate language. It's not quite the same syntax, but there's work to make this fit closer and closer to the intermediate language. And there are lots of people involved in that project. So this is also a very exciting direction. So there's a lot of academic research in that direction, and there's a close interaction with the Rust community. So a very long-term goal would be to have a verified semantics for all parts of Rust. So the surface language, the intermediate language, LLVM, and WebAssembly. But let's start slowly. So one of the nice things about the Rust language is you can actually see this as an onion. There's a very safe subset of Rust, and this has recently been isolated in the Hexpack, the high assurance cryptography specification language, all the way to unsafe Rust. And the various languages in between, and the various projects also to try to make these in-between languages precise. But we're only going to focus on the real, the inner parts of the onion. So the first steps is we're going to have a look at Hexpack, which is a pure subset of Rust. And then Fiat Rust and Bedrock, which is a way of generating. This is a small imperative language, which is mostly used to generate high assurance cryptographic implementations, and then a pure or functional part of Rust for smart contracts. I should say here, I'm talking about pure programs, as you saw in Thomas's lecture. He used state, so there seems to be something off, but we're looking at pure functions that take a state and output a state again. You can think of this monetically if you're so inclined, but they're pure functions, so functions without side effects that take the blockchain state and produce a new blockchain state. So let's first look at Hexpack. So this was a language that was designed for high assurance cryptography. So I should first explain what is high assurance cryptography. So this is cryptography that is functionally correct. So you actually implement the crypto correctly, mathematically correctly. It's cryptographically secure. This typically means that if you could break such a cryptographic construction, you could also solve a long-standing open mathematical problem. It needs to be fast, and otherwise, So this is a very important requirement, obviously in practice. It needs to be constant time, so you don't have, and more in general, you want it to be resistance against side channel attacks, timing attacks. Now, if you look at the IETF way of standardizing cryptographic, well, generally protocols, but in particular cryptographic protocols, they have a bunch of imprecise pseudocode. Now the proposal by Hexpack, which I really like, is just to use Rust as the specification language. And quite a few examples have been worked out in Rust. But what is nice is it's a subset of Rust, which has a very precise operational semantics. It has a type checker. What I'd like to see is that Hexpack is actually blessed by the by the Rust community, so that people from the Rust community, they look at the Hexpack and see, well, this is actually what we meant when we implemented Rust, because the type checker of Hexpack is different from the main one. So there could be a difference, but we trust it to be correct. There are backends for a number of proof assistants. The people who initially developed it, they come from the F* community. So this is a proof assistant very much like the COG proof assistant that I'm talking about, but it's developed by Microsoft, and it's inspired by the by Microsoft's F# language that you may also have heard about. It has also a backend in the EasyCrypt system, which is a proof assistant mostly targeted for cryptographic operations. And then what we've recently done in my group, this was done by Milo. He actually made a backend in COG, and this gives a lot of new possibilities that I'll soon talk about. One thing one can do is, if we're looking at elliptic curve cryptography that Diego will tell you a lot more about in the next lecture, instead of just doing property-based testing about the group laws for these elliptic curves, you can actually prove them now, because you have your program in Rust, and you translate it to a proof assistant, and then you can actually make a mathematical proof that it always satisfies these mathematical laws. Examples are the well-known examples, SHA-256, but also, and this is recently done by 2 bachelor students, and this is jointly supervised with Diego, so Casper and Matthias. They implemented the BLS elliptic curve, and this is a pairing friendly curve. Diego again will say more about this, I expect. There's now a standardization proposal by the IETF, and so one reason why we're interested in this is that this is used in the Concordium identity layer. So what we want to do is use Rust in the standardization of these BLS curves, and then so that we actually know that we've implemented the right thing. But there's more. Just specifying, of course, is not enough. So the other thing we want to do is, now that we have the specification, we want to create fast code. We could do that by hand, but then you could make a programming mistake, and this is done even by very clever people, very experienced programmers. So there's now a very nice toolchain to actually take this out of your hands. So this is the Fiat Cryptography project from MIT. What this does is it generates platform-independent, correct implementations. And it does so by taking a small language in the COG proof assistant, and then use a verified partial evaluation, or you could call it a verified compiler, to a small imperative language. Now, this small imperative language is a subset of the Rust language, so you can print it in the end to Rust and actually generate Rust. And this is now standard part of the toolchain. So we can now write our code inside the COG system and then generate fast implementations in Rust. And we know that these implementations are correct. We know that they're constant time. So this is a way of generating high assurance code. Our PhD student Benjamin, he implemented field inversion in a very efficient way, and our research assistant Rasmus, he implemented the BLS curve in this way. And Diego again will say more about this. One thing that's missing is that the Fiat cryptography pipeline doesn't have loops and functions calls. Doesn't have loops and function calls, and it cannot, because then it would you would not have straight line code. So it could be a it could be vulnerable to timing attacks. But we use an extension of this called Bedrock, and that can actually do that. And then you need to check by hand that it actually stays constant time. So this is what we're doing, and we're now building this whole infrastructure to generate high assurance crypto in Rust. And as a side product, side product of this, we can also generate this in C, Go, and Java. Now, what I spoke about before is implementations of cryptographic primitives. But if you look at things like they're big, so they're more complex protocols like TLS and noise, and they have become a very popular verification target after the Heartbleed attack. And TLS, the open TLS implementation, was actually full of just riddled with bugs. There's a very big project by Microsoft India and the French Research Institute, and they prove functional correctness of C code in F star. There's also a proof of that verified C code and proved the HMAC construction to be cryptographically secure. One thing that came out of this is that the usual way the cryptographers do proofs, it doesn't scale to large protocols like TLS. So they actually came up with a new methodology to do this. So this is called state separating proofs. And what we've done is this is a way of doing this on paper. So what we've done is to translate this into a library inside the COG system, so that we can actually reason not only about pseudocode, but we can actually reason about real implementations. This is a paper that was well received. We just got a distinguished paper award for this at the Computer Security Foundation's conference. So all these things that I've now mentioned could be possible building blocks for the verification of things like Rust TLS, Rust noise, and some other complex protocols. Some other protocols one could think of is one thing we've already done, and this is with my PhD student Nikolai. He analyzed Sigma protocols for zero knowledge, which are used in the ID layer of Concordium, and there we can actually reason about the actual implementations and prove that they're cryptographically secure. Also in this line of work, we have the first formal proof of safety and liveness of a Nakamoto consensus protocol, and this is the protocol that's used by Concordium. So we know that no bad things happen, and we know that always eventually good things happen with the consensus protocol that's used by Concordium. So now with this whole big library that we've set up, so we take the pseudocode from IDFF, we translate it to Hexpack, we just implement the pseudocode, then we go to the COG proof assistant, then we use the Fiat library, and we actually generate Rust again. So we start from Rust, and then we generate more efficient Rust from this. So I'm quite excited that we can now use this language at the two ends of the going from specification to implementation. And one thing that we're working on now is a case study to go from the BLS specification to generate an efficient implementation, and we're really close to having that. Now you could say, well, this is all very nice to want to have mathematical proofs that your cryptographic constructions are secure, but this is actually used in production. So Concordium is using it in production. It's used in the Linux kernel, it's used in WireGuard, it's used in MirasOS. So this is something that's really ready to go from academia into production. And as I said, so Concordium is one of these companies that's very fast to pick up these new ideas from the academic world and to translate them into practice. This is also because we have quite a few people with PhDs working in Concordium. So smart contracts, you've already had an introduction to this from Thomas. These are small programs on the blockchain, and Concordium uses WebAssembly on-chain and Rust to generate WebAssembly. And they can automate. These are the same examples that Thomas mentioned. they can automate simple banking tasks like what is called distributed finance. So you can make custom tokens, or you can use GTUs. You can have an exchange. So if I have my kind of token, I can exchange it for your kind of token. Escrow, we have a voting. So these are small scale voting, something called boardroom voting. We've implemented all these things inside our sorry, I'm running ahead of myself. So these are some of the standard examples of smart contracts. Now people have been playing with these in legacy languages and without being too careful about using formal methods. And there have been very big hacks. So well-known ones are the DAO, something called Uniswap is an exchange. There's another one, BurgerSwap, dForce. I give you a small picture of the value of dForce, and this one goes up to 25 million, and then suddenly someone takes all the money out. So if you actually want to do these kind of big applications on a blockchain, you better use a well-developed language like Rust, so that you don't have compiler problems like you have in Solidity, and you better use formal methods, because actually some of these contracts were actually audited, but the auditing didn't find didn't find the bugs in these smart contracts. So what we've done is to develop a certification framework in the COBRA assistant. So what you do is you write a specification, and by writing this specification, that's something you should do in any case if you have a smart contract. We found bugs using the quick check tool that's also used in Rust. And you can also prove adherence to the specification in COBRA. Going back to Thomas's example, player one has always has a winning strategy in tic-tac-toe, something you could prove. So what we have is a mathematical model of, I'm speeding up a little because I'm running out of time. We have a mathematical model of smart contracts as interacting pure programs. But the mathematical model is nice, but we actually want to have something running on chain. So what we do is we take those programs that we have in our mathematical model, and then we can translate them to a number of other languages. So this is well known for Haskell, and this is a very well-known well-known way of getting correct programs in Haskell. But we can now also do it for the Rust language. So what kind of specifications could you give for such a program? So here's, for example, the type of the reverse of a list. If you're familiar with Haskell and familiar with liquid Haskell, then you could look at the pre and post conditions of the reversal function. Say I have a list, and then the length stays the same if I reverse it. I'm saying verified extraction, so translation from the mathematical model to Rust, because we actually did the whole thing with metaprogramming. So we actually know that the translation is also correct. So how can you translate functional programs to Rust? Because Rust doesn't have a garbage collector. So what we do is we use Rust's arenas, and this is a good model for. So we leak all the memory in one go. So the memory is freed after the program terminates, and this is because smart contracts typically don't use a lot of memory, and they're fairly simple programs. And what we've done is actually create something that's already running on the Concordium StageNet. So some conclusions. We can go from a specification in Rust in Hexpack to an implementation in Rust in high assurance crypto. We're developing high assurance cryptography in Rust, and we're working with the Rust formal verification working group that we're helping to revive, and the Rust crypto interest group. We're using smart contracts in Rust, and we actually have verified a number of smart contracts in Rust, and we can make mathematical models of these smart contracts and find bugs and show that there are certain bugs that cannot occur. As I said, Concordium is using high assurance crypto in production, uses WebAssembly that has a formalized semantics and uses verified smart contracts on the StageNet already. So thank you for your attention.
Thank you very much, Bas. Crab emojis, clap emojis, chain emojis, please, for Bas. Thank you very much for that. We're definitely going to have to get your slides out to people, because I think the way the screen share has shrunk your slides, even though you did use very big fonts like I asked you to. Thank you so much. We're going to get these slides out to people, and I'm sure we're going to have you back again to talk some more about formal verification in Rust. But thank you so much. Let's take some questions. Please direct your questions to the stage Q&A, and please tag the speaker using the @ symbol. Any questions?
We go to chat.
Yes,
Q&A.
yes. Just seeing if there are any specific questions. A good question would be, and I think you can cover this as well as Thomas, our previous speaker, is how zero knowledge proofs are used in the ID layer, and how are they verified for their correctness.
So that's a whole talk, and
yes.
So they're very nice talks online. I recommend you to look at the I mean I could try to explain this, but there's a very nice talk by Ivan Langgaard online on the Concordium YouTube channel, and I'm sure one of the others can find it now and give the link. And he explains it so beautifully that I mean he takes 10-15 minutes to do so.
Yes. Okay, so we have a question from Giles.
Yeah.
How much time does it take to prove something? Is it days, weeks, or months?
So to prove simple things, it's days. To prove more complex things, it's months. But a lot of things can be reused. One nice thing, so to build a whole framework could easily take up to a year. But then we saw some of these. So we built both the verification framework and the testing framework. I was having coffee, reading the news. I saw, well, again, one of these DI5 projects, they made a mess. So I talked to Milo and said, well, I think we can find this. He ran the test, found it in 10 minutes. And this was something that went through 13 weeks of auditing. So, this gives you an indication that once you actually build the whole framework, you can do things very quickly.
Okay, so the heavy lifting is done.
Important part of both the standardization and certification and auditing process, and these things take time.
Right.
As Diego says, who audits the auditors? So that's
Yeah, absolutely. So I was just saying that the heavy lifting is actually done in building and crafting the framework. But once you have that, it's a very powerful tool beyond any kind of auditing that can be done. And for something with money, dealing with real financial consequences, you want to have the most granular form. You want to have the most granular form of checking and verifying that everything is correct as possible. So that's really great. Okay, we have a question from Eric, another one of our co-organizers.
So this is the general context of oracles, and it's it's on the roadmap. I think I think Bainey can better answer this at the AMA later, but that's certainly something that people are working on.
Yes. The question is it possible to get information outside of the Concordium blockchain in the smart contract? For instance, paying funds based on who won a football match, and how is the external data verified? Is there any plans on being able to build a framework for information that's streaming into the Concordium blockchain to make sure that that's been verified as correct and truthful?
So that's something that could be done, but I mean, so what you verify is typically a mathematical statement, and not something from the real world. So you would take the data from the real world at face value. Of course, then you can use the regular way of verifying whether something happened in the real world that we're used to from journalism or other topics.
Amazing. Okay, thank you very much, Bas. It's been a great honor to have you here, and congratulations on. Oh, okay, we have one more question from Giles, and then this will be it. Which DeFi protocols have gone through formal verification, if any?
So
that you know of, Bas.
As I mentioned, we did. Oh, maybe I didn't say it. We've done escrow, a voting protocol, a Congress. So this is basically a distributed funding agency. We have a verified exchange. So we have quite a few. If you look at the concert website, you can find all these contracts. But basically, we have verified instances of all the Paradigm smart contracts, and we're now working with the company to actually generate more and more smart contracts on chain.
Great. Thank you very much, Bas. Again, congratulations on your recent award from the IEEE on one of your papers as well. And thank you very much for giving us this great talk. We're going to get your slides and share that with people, and also the recording as well. We'll try and do something with that as well. But thank you very much, Bas. And crab emojis, clap emojis, chain emojis, please, everyone. Show your appreciation to Bas.